Okay, so now we're going to talk about the two case studies for cost-benefit analysis today. First, terrorist attacks targeting highway bridges, and secondly, sewage overflows at wastewater facilities. So the scenario here is that terrorists might want to wreak havoc by targeting highway bridges with a bomb that would then cause a bridge to collapse. And there is a countermeasure available to this, which is to harden the bridge so that even if a bomb were to target that, it wouldn't actually cause a collapse because it's been reinforced. And so DHS has been considering whether or not it's feasible to do this, and so we can use standard cost-benefit analysis techniques to see under what circumstances such hardening investments could be justified. And I should say that this study comes from some research done by John Mueller at Ohio State, and the paper is available for you to read in the reading. So, first step is to estimate P0. Okay, so this is what is the a priori probability that a terrorist would try to target a particular highway bridge. Well, this is a hard one to estimate because there have been no known instances of this occurring in the United States, at least. So we can maybe start by assigning a very small probability, so like 1/10,000th of an annual probability of this occurring. Then we'll move on and say, okay, let's think carefully about what the cost could be if there were a successful attack. Well, if you look at the cost of emergency bridge replacements or following previous collapses due to accidents, or the average was about $40 million. So, and then we have to consider the conditional probability of that occurring. Well, if the terrorist is going to actually bomb the bridge, then it will have collapsed. So the conditional probability there is 1. You're definitely going to have to pay to replace it. Then looking at loss of life, all right, so you can put a dollar amount on the loss of human life. And so the standard actuarial value used in government is around $6.3 million. And the average number of lives lost whenever lives were lost in a bridge collapse in the past has been 80. And only about 20% of the time were lives lost. And so our conditional probability is 0.2. For simplicity, those are the only two loss categories we'll consider. Then we'll try to estimate what the security costs are, or just be given as input for the proposed countermeasure. So what we'll do is say that the bridge retrofitting has been estimated to cost sort of 20% of the overall bridge replacement cost, but we can amortize that over 25 years, so it's about $260,000. Then finally, we can just estimate the risk reduction rate. It's going to be taken to be R equals 0.9. So this means there's a 90% reduction in the risk of an attacker who tries to bomb one of these bridges. So this is again somewhat of a guess, but we're selecting it in order to give the benefit to the best possible chance of our benefit exceeding the costs. So there you have it. We can fill in our equation. So I encourage you to pause the video and go back and fill this equation in for yourself. And when you're ready, press play, and I'll advance to the next slide. Okay, here it is. So, P0 gives 10 to the minus 4 times 0.9 times those two expected losses minus the $260,000 to spend to reduce this. And it turns out that the expected net benefit is strongly negative. So this says for at least these assumptions and these parameter values, this is not going to break even. So the investment does not seem to be justified. So now we'll go on to the second case study, which is dealing with sewage overflows at wastewater facilities. I want to mention this for a couple of reasons. You can see the paper and read about it in the reading. This particular case study here and resulting paper actually began as a course project for this class several years ago. So the students who were taking this class they had been doing research on developing an attack detection system on critical infrastructure systems, and so they wanted to do a cost-benefit analysis to justify the security investment. And so this is ultimately what we came up with through this class. So first thing was to estimate P0, so the a priori probability of an attack on one of these wastewater facilities. Well, the original goal was to do that, to try to estimate the probability of malicious attack triggering a large overflow. But unfortunately, if you go back, well, I guess fortunately from a societal perspective, but unfortunately from a researcher's perspective, there was no real history of this occurring. So at least in terms of publicly reported attacks. So we actually revised the goal to instead look at the probability of an accidental sewer overflow, which could be triggered by, all kinds of reasons besides attacks themselves. And so the accidental overflows can be detected, and it so happens that for the incident detection system under consideration, it can detect and prevent both accidental and intentional overflows. So the security control had this safety benefit. So we went digging for data, and what we found was that the California Water Board actually published information on the number of overflows they were having. There were 46 large overflows in 1 year across the whole state of California. Elsewhere, we found that California's wastewater infrastructure consisted of 110,000 sewer miles. And so from this, we could do a sort of empirical point estimate of the probability of having an overflow in terms of the number of sewer miles available, which is just 46 divided by this 110,000 sewer miles. So there's our P0 estimate. And then we also found that cities across the U.S. with population over 100,000 miles have an average of 1,300 sewer miles in their facilities. So we get to our final P0 for the average U.S. city to be 0.541. So that means that in any given year, there's around a 50% chance that there will be a large overflow in the average U.S. city. So in this case, we're saying I keep referring to this as probability, but it's the expected number of overflows. So it could be the case that P0 is greater than 1 if the average number of overflows is per year is 1, greater than 1. So we've enumerated P0. Next, we're going to look at the losses, right? So and then estimate what those costs are and their conditional probability. So we sort of set out and enumerated all the different loss categories we could think of, and they were divided into the direct losses and indirect ones. There are things like the actual direct cost of cleanup, the cost of property damage from the overflow, regulatory fines, which sometimes occur, but there's also lost business for the victims because they can't operate. If the overflow impacts a business, they can't operate whenever this is happening, and also the health cost to victims. But there's also indirect losses, which are parties that weren't directly affected by the overflow but could still indirectly be harmed. So you have like lost business for non-victims. So maybe your property didn't overflow, but you're next door to somebody who did. Well, if you're running a business, people likely still aren't going to come. At least some of them won't. Then there's the broader environmental impact of these adverse events and things like psychological distress. And we can see that for some of these categories, we can measure reliably with some data. In other cases, we can't. And so what we're going to do is just our best effort and estimate the costs in the categories where we can have data. And that will provide us with a lower bound for what the true total cost actually is. So here's what it looks like in table form. We got this from looking in various sources through records of court cases, public records of EPA fines, and so forth. So what we found is the cleanup cost for an average large overflow is around $22,000. This has a conditional probability of 1. I think this is almost certainly an underestimate, but it's the best we could find. Property damage, about 1.4 million, but it's not always the case that there actually is a property damage that's incurred by this. And so we don't really have any data on the conditional probability, but we sort of arbitrarily selected 0.25. And then lastly, we have we have pretty good data on when the EPA finds organizations in California. So we estimate that to be $2.89 million with a 1% conditional probability. So how do we get this? Well, we got the $2.89 million by looking at all of the EPA fines, taking the average. For the conditional probability, we looked at the fact that there were 46 violations in the state of California over the 12 years from 2000 to 2011. That was 46 violations across the U.S. In which case the EPA levied a fine. And then secondly, what we have is that within California, we know that there were 46 sewer overflows just in 1 year, in 2012, and that California represents around 12% of the U.S. population. So you normalize that by 12 years, then you end up with this 0.01 probability. So there's roughly a 1% chance for a given overflow that the EPA will issue a fine. Then we can carry on and actually go out and look at different cities which will document their basic infrastructure for wastewater collection and processing. And from that, we could identify the approximate sewer mile lengths that each used. And it varies very widely, not just by population, but often because of sort of geography. So there are some cities that have relatively fewer sewer miles, like San Francisco, but then others, such as Atlanta, which have a lot. So that allows us to then estimate what the security cost should be. And the reason we can do that is by looking at their sort of infrastructure. We can identify what kinds of which points we would have to place our intrusion detection system, and so some systems are more complicated than others. So the city of New Orleans, for instance, is very complicated because it's below sea level, and so there's a lot more involved system in place that would require more active monitoring. Right, so then we take an estimate, or in this case take as input, the risk reduction rate R. So we're going to assume that we get a 40% risk reduction, and the reason we're going to say that's plausible is that we would expect that this system could detect some overflows soon enough to stop them from actually leading to a damaging overflow, but that there are going to be others that couldn't be prevented even if you were able to have an early warning that they're coming. All right, so given all that information, I want you to sort of circle back through your slides and calculate the expected net benefit in this case. And pause the video to do so, and then come back whenever you have an answer and hit play. Okay, you should have an answer now, and this is what we have, and that works out to be $67,000. This is for the average city, okay? And so for the average city, the mythical average city in the U.S., the expected net benefit is positive, so given the costs, it's actually worth making the investment. Now what we can do is we can go back to our reference point here for different cities, and they each have different costs and sewer mileage, which affect the probability of occurrence and what the costs of countermeasures are. And we see that in some cities, like Atlanta and D.C., it's clearly beneficial, whereas in other cities, it's less so. Either because of the higher cost of the intervention or the lower probability of incidents due to this fewer number of sewer miles. You can sort of visualize this here using R, of course, where we're plotting on the x-axis the number of sewer miles in the city, and then on the y-axis the number of the cost of the countermeasures. Right. So it so happens that in the cities that have relatively more sewer miles, which may make an overflow more likely, then they tend to have a positive return. But where cities that have higher countermeasure costs, they tend to be less likely to have a positive return. Okay, so that wraps it up for video 2. When we return for video 3, we can talk explicitly about how we'll deal with some uncertainties in the calculations that are usually present. Thank you.